This is a large industrial furnace that's used for melting steel. Like all furnaces, it needs a source of heat. Here, the heat is produced electrically. It all happens when these two carbon rods get closer to the surface of the metal. Between the end of each carbon rod and the metal surface, we've formed an electric arc. These arcs provide sufficient heat to change the steel from a solid to a liquid. Here's a more familiar use for an electric arc as a source of heat: manual metal arc welding. In this process, the heat is needed to melt the edges of the metal we're joining together. But an electric arc isn't the only source of heat that's used in engineering. Here's another: a flame. To be more precise, it's a gas flame. This is the process of gas welding. Again, the heat is needed to melt the edges of the metal we're joining together. We're also using a gas flame in this joining process, brazing. However, the gas involved is different. A gas flame is often used as a source of heat in other engineering processes, heat treatment, for example. This furnace is heated by a number of flames along both inside walls. And in a similar way, flames are used as a source of heat in this large industrial furnace. To make sure the temperature of the furnace is uniform, it's heated by a whole row of flames all round the inside. These are the gas pipes going into the furnace. From the number of them, you can get some idea of the amount of gas that's involved. Here's another process where a flame is used to provide a source of heat. It's known as flame cutting. In this process, the heat is not sufficient to melt the metal being cut. It's needed only as an aid to cutting. A flame is the source of heat in a blacksmith's forge. He can use the flame to heat components to a very high temperature. In this case, to white heat. What he's doing here is forge welding. In the case of an electric soldering iron, the source of heat is quite different. It's produced in the same way as in an electric fire, as a result of electrical resistance. If we look inside this soldering iron, we find two small heating elements. Pass a current through them, and they get hot. Here's another process where heat is produced as a result of electrical resistance. It's a form of resistance welding known as spot welding. This gives us three main sources of heat: a flame, an electric arc, and an electric resistance. Let's look at some of the heat sources we use in more detail. In a forge like this, the flames are produced by burning a solid fuel, coke with a plentiful supply of oxygen. The oxygen is supplied from a blast of air which is pumped into the coke by a blower behind the forge. Now, the temperature of the fire is controlled by the volume of air blown through it. This can be adjusted by a damper. With the damper out, the volume of air is increased. This has the effect of increasing the temperature. If there's sufficient oxygen, we can easily get the temperature of the fire up to well over 1,000 degrees centigrade. From a solid fuel to a gaseous one, natural gas or town gas. Here, the fuel is burnt with oxygen from air supplied by a compressor. The gas and air must be mixed together in the correct proportions in order to achieve efficient combustion. We often use a natural gas and compressed air flame for brazing. If the mixture of gas and air is correctly adjusted, the temperature of this flame can be as high as 1500 degrees centigrade. Using a different gas as fuel, we can produce a flame with an even higher temperature. Here we're mixing together pure oxygen supplied from a cylinder with a gaseous fuel called acetylene. Again, in order to achieve efficient combustion, the acetylene and oxygen must be mixed together in the correct proportions. We now have what's called a neutral flame. This is the type of flame that's normally used for welding low-carbon steel. The temperature of an oxyacetylene flame is over 3000 degrees centigrade. The heat that's needed in flame cutting can be produced by burning any one of several different gases. Here, the fuel is propane. It's burnt with pure oxygen, which comes out of a cylinder. The flame is carefully adjusted until there's a series of short, blue, luminous cones. That's the heat source. To cut the metal, we use a high-pressure jet of oxygen. You can just see it in the middle. This oxygen is supplied from a separate cylinder. Now, in this process of cutting metal, the steel being cut doesn't melt. It's removed by chemical action. The chemical action is brought about first by heating the metal to a bright red heat. Next, the high-pressure jet of oxygen is directed onto the heated metal and immediately oxidizes it. The oxide formed has a much lower melting point than the steel being cut. The temperature of this heating flame is sufficient to melt the oxide, which is then blown away by the jet of oxygen. Another important source of heat is the electric arc. In the case of manual metal arc welding, the arc is established between a specially coated electrode and the workpiece. We can see how the arc is formed in this diagram. We'll connect the workpiece to one side of a suitable power supply, the electrode to the other. Now, if we touch the workpiece with the electrode, we complete the circuit. If we now try to break the circuit, the metal of the contacts vaporizes and an arc results. This is what an electric arc looks like in slow motion. The temperature of the arc is between 4,000 and 5,000 degrees centigrade. This is sufficient to melt both the metal of the job and the end of the electrode. One great advantage of using an electric arc as a source of heat is that it produces a lot of heat in a very small area. This coil of wire will offer a high resistance to the flow of an electric current. If we pass a current through it, it becomes red hot. If we disconnect it, it cools down. The heating effect of an electric current is used for many heating applications. This furnace is heated by passing an electric current through a number of high-resistance coils all round the inside. the heating effect of an electric current can be sufficient to cause a conductor to melt. This is the principle of the fuse. Spot welding depends on the heating effect of an electric current as it passes through the join. Let's see a spot weld being made in cross-section. The action has been slowed down. The join is held between two electrodes under pressure. As the current passes through, it meets resistance and heat is produced. The heating effect is greatest at the centre of the join. A combination of heat and pressure results in a nugget-shaped weld. In many engineering processes where heat is involved, it's necessary to have some means of measuring temperature. For example, in this process of heat treating, it's essential to know the temperature of the components in the furnace. To measure the temperature in this furnace, we're using a special device known as a thermocouple. This measures the temperature electrically. The reading is recorded on a suitable meter kept well away from the furnace. Let's find out how a thermocouple works. Here we're joining together two wires, each made of a different material. In this case, one is constant tan and the other copper. The other end of each wire is connected to a sensitive meter. Now let's see what happens if we heat up the junction. If we look at the meter, we see the heat is causing a small electric current to flow in the circuit. The higher the temperature, the greater the current. Here's a small industrial thermocouple. Inside this protective cover are the two wires. At this end, the cover has been broken. Here, the two wires join. If we heat the junction, the temperature is recorded on a similar meter, this time calibrated in degrees centigrade. The particular metals used to make a thermocouple depend on the temperature you want to measure. Can you find out what metals would be suitable to measure the temperature of molten steel? Here's another process where temperature is important: hot forging. It would be difficult to use a thermocouple here. However, in this case, the temperature can be measured by another device known as an optical pyrometer. It looks rather like a telescope, and this is what he sees when he looks through it. The small disc in the middle is the color of the component. Running through the disc is a piece of wire, which can be heated by an electric current controlled by this knob. As we increase the current through the filament, it changes color. The object is to make the wire the same color as the component. This will have the effect of making the wire disappear. Well, almost. All that remains is to read the temperature from this dial. Another method of measuring temperature is to use heat-sensitive crayons like these. These crayons change color when heated to a specified temperature. This one, for example, will change from blue to white when the temperature reaches 600 degrees centigrade. Let's try it. See how the colour's beginning to change? The temperature of the surface is now about 600 degrees centigrade. But if we heat a piece of polished steel, we don't need heat-sensitive crayons. This chisel has been given a polished surface. Let's see what happens when we heat it up. There's a band of different colours moving down over the surface of the metal. We can use these colours to estimate the temperature of the material. Here we're tempering. The right temperature is reached when the tip of the chisel turns blue. There, now it's quenched. If we look at the chisel now, we find the colours have been trapped in the surface of the metal. Here's a typical tempering chart. It tells you which colours correspond to which temperatures. This is a fusible cone. It's made from a special material which will cause the cone to collapse when it reaches a specified temperature. By varying the constituents, we can produce a series of cones which will collapse at different temperatures, in this case in steps of 5 degrees centigrade. We can use these cones to check the accuracy of other devices employed to measure temperature. For example, the thermocouple in this furnace. In the case of these 3 cones, the one in the middle is designed to collapse at 800 degrees centigrade. The other 2, 5 degrees above and below that temperature. At the moment, the temperature as measured by the thermocouple is just above 600 degrees centigrade. Let's raise it. See how the cones are beginning to collapse. According to the thermocouple, we've now reached 800 degrees. And this is how the cones finished up. Remember, it's the one in the middle that's sensitive to this particular temperature. Can you find out if it's collapsed by the right amount?